All right. So what are you gonna cover for us today?
Well, are you ready for me to go ahead and jump in?
Yeah, share your slides. Let's see. You can give an intro to your talk.
I should be sharing my screen right now. Can you see it?
Yeah, it looks great. So take it away.
Excellent. Thank you so much. As you know, my name is Matthew Cruz, and I am incredibly excited to talk to you today about mathematical planning and F sharp. Now, as I've worked with different companies and in different industries, I have found that there are three questions that really drive organizations and businesses. The first question is, what happened? We look to the past to try to understand how did we get to where we are. The tools for this are things like, you know, dashboards, pivot tables, statistics, all these different means of analyzing our data to understand what happened in the past. The next question is, what will happen? We need to make a prediction about what we think is going to occur in the future. And one of the fantastic things that you've been seeing today is that F sharp is an amazing language for machine learning, which is a powerful set of tools for being able to take data and create predictive models which help us make inference about what is going to happen in the future. But there's a third question. And that third question is, what should we do? And it's this question that I really want to focus on today. Now, as I've worked with different people and worked on answering this question, what should we do? There's always three key ingredients. The first is there's a quantifiable objective. There's something we're trying to achieve, and we have a way of measuring it. It could be maximizing profit, minimizing cost, maximizing efficiency, or minimizing waste. Whatever it may be, there is a way that we quantify success. The second is constraints. These are the limitations on what is possible. They could be financial. We only have so much money to invest. It could be people. We only have so many developers to assign to projects. It could be legal. There's only certain things we're allowed to do. But there's always some type of limit on what is possible. Lastly, there are decisions. These are the choices that we need to make within this framework. It's what we need to decide in order to create a plan going forward. Now, wouldn't it be fantastic if there was a set of tools for answering the question, what should we do? We have tools for inspecting the past. We have tools for predicting the future. But wouldn't it be amazing if there was a tool for answering what should we do? Well, fortunately, we do. It's called mathematical planning, and it's actually been around for decades. Now, this begs the natural question, okay, Matthew, what is mathematical planning? I don't know what it is. Well, I could give you a very clinical response. It's a discipline of finding values for a set of decisions that achieve the best possible outcome, given some quantifiable objective and constraints to be adhered to. Clinical, true, or the definition I prefer is it's the mathematics of caring for people. When I was teaching this at university, students would come in, and on the first day, I would say, all growing up, we always ask, like, why do we have to do this math? Why do we have to do this math? And when it came to this class, I said, this is why. Mathematical planning, I think, is one of the crown jewels of mathematics. And it allows us to do the most possible good with what we have available. Now, a new question may arise. Okay, Matthew, you've piqued my interest, but how do we actually do mathematical planning? Great question. Well, the workflow is first we build a model. A model is a kind of mathematical representation of our problem. It includes that objective and the constraints and the decisions that we need to make. We then send that model to a solver. And a solver is a piece of code that knows how to understand that model and search for the possible solutions. And because of the way we structure the problem, it's guaranteed to find the best possible answer. And finally, we get the result back and it tells us what values we should use for the decisions. This is how much money you should invest. This is how many people you should put on the project. Now, what are the ingredients that make up a model? Well, first of all, there are the sets. Sets are the dimensions of your data, how it's organized. It could be the cities you're planning on sending material to. It could be the products that you're planning on manufacturing or selling, or the time periods that you need to plan over. There are parameters, which is the data that goes into the model. And these are things like, what are the capacities of my different facilities, or what are the demands I'm seeing in the market, or what are the production rates of the different facilities. Then there are decisions. Again, these are the choices that we need to make. And we can think of this as like a knob or a dial that the solver can adjust to try to find the best possible plan. Next, there are constraints, the limits. And these are mathematical representations on the limits of what are possible. So it could be like, we only have so much money, we only have so many people, so you have to stay within those bounds. Lastly, there's the objective. It's how we measure success. And so we give it the expression that we want the solver to use to measure how well is it doing. Let's talk about some examples. The first one comes from the power industry, where we need to make a plan for producing and distributing power. The sets in this case would be power plants, where we can produce power, and cities, where we're sending power to. The parameters would be the cost of generating power, the cost of transmission, what the city's demand for power is, and what the capacity is of the power plants. Decisions would be, how much do we produce at a power plant, and how much do we send along the different transmission lines? Constraints are, you can only produce so much power, and we do need to actually power the cities. And our objective in this case is to minimize the overall cost. We could also look at the logistics industry, where we're shipping packages. In this case, our sets are the packages we need to deliver and the means we have for delivering them. The parameters would be the dimensions of the package. How big is it? How heavy is it? And the capacity of our shipping methods. The decisions would be, okay, I'm going to put this package on this shipping method. Constraints in this case would be, we can't overload any of our shipping methods, and we have a budget. And so we can't exceed that when it comes to choosing methods for shipping packages. And our objective would be to maximize our on-time delivery to create a great customer experience. Some other examples real quickly is the sports industry. Scheduling seasons. I actually know that the National Football League, so American football, schedules its season using mathematical planning. There's also the finance industry, where I've actually worked some. The beginning of this conference, Don Syme showed a slide and on there was Rocket Mortgage, and I actually worked there for a while. And we had a really interesting problem, and I apologize for having to be a little coy and a little vague, but we had some financial decisions that were being made by people using some manual methods. And it took 4 hours for them to do it. So we were able to come in and we developed a model. And what that model did is it took that 4-hour process and turned it into 10 minutes. And not only was it faster, it was much more profitable. So that's part of the power of mathematical planning. And these types of problems are all over the place in finance. There's also a unique application. This is one of my favorites. I was talking with a company, and they actually would use mathematical planning to create meal plans for families. A family was able to put in, these are my allergies, and this is what I have for cooking, and this is what my budget is. And then the model would decide, hey, this is what I think you should buy, and this is what I think you should make in order to maximize the nutrition and the well-being of that family. So again, mathematical planning isn't just about making money, it's about caring for people. Now, what I've been trying to get across to you is that anytime you have a quantifiable objective, constraints to be obeyed, and decisions to be made, you may very well have a mathematical planning problem. Now, let's actually work a problem and let's see some code. This has all been very nice, Matthew, but show me the code. Well, let's do it. And we're going to work a problem that's very pertinent these days, and it's vaccine distribution. We have a set of trucks that are able to distribute the vaccine, and we have a set of cities that need the vaccine. Each city has a different amount of vaccine demand. Each truck has a different capacity, and the cost for sending a particular truck to a given city is variable. So that cost is going to change depending on which way you're having it go. And we want a plan that's going to minimize the cost so that as time goes by and we have to continue to do this distribution, we're saving money. Now let's look at our data. First of all, we have trucks. And right now I'm just modeling this as a list of strings. We have our cities, again, a list of string, and this is where we need to send the vaccine to. And we have demand. And right now I'm putting this in a dictionary where the key is the city, and then the value is the float. The value is the demand for the vaccine. We also have capacity. So for each truck, there's how much of the vaccine it can carry, and the cost. And again, the cost is keyed by a tuple of city and truck and the cost associated with using that method. Now let's start building our model. We have to make assignments. So what we're going to do is we're going to assign trucks to cities. So for each truck and for each city, we are going to create a Boolean decision. So a 1 would indicate I am not sending this truck to that city. And a 1 would indicate, yes, I am sending this truck to that city. I now need to create some constraints. So each truck can only be used once. It's not possible for a truck to physically go to multiple cities simultaneously. So these are my single assignment constraints. For each truck, I want to sum the total number of times that truck has been assigned. And I'm going to use a list comprehension and I'm going to sum it. So for each city, I am going to take whether I was assigning the truck to that city and I'm summing those all up. That sum, the total number of times it's assigned, has to be less than or equal to 1. So this will tell the solver, you can assign a truck once or not at all, but that's it. Now we need to make sure that our cities are actually getting their demands met. So I'm going to create some city demand constraints. For each city, I'm going to sum the supply that is being given to that city. And to do that, I'm going to sum a list comprehension. So for each truck, I'm going to multiply the capacity of that truck by whether I actually assign the truck to that city or not. That sum has to be greater than or equal to the demand of that city. Now, we create our objective function. So this is the expression that tells the solver, this is how I measure success. In this case, I'm going to, again, sum a list comprehension for each city. And for each truck, I'm going to multiply the cost of using that connection by whether I actually am using it or not. The objective then takes that expression and says, hey, I want to minimize this function. Now we can build up our model. Our model is simply create the model, given that initial objective, add the trucks assigned once constraint, add the city's demand met constraints, and then we're going to call solve. And so this would send the model to the solver, and the solver would search through that and find the best possible plan, which minimizes the cost, only assigns the trucks once, but still meets the demands for the city. Yay, that's fantastic. What's powerful is as our data changes, we can rerun this and reuse this model. Now, you might be asking a different question. Okay, Matthew, mathematical planning sounds cool, but this is an F# conference, but why F#? What about F# makes it, cool for this type of thing? Well, to answer that question, I need to point out there's actually 2 bugs in that code, 2 visible bugs. Now, there's always someone who's very astute and may have noticed them, which is great. But what's really important to know is that the compiler can't see them. It cannot help you. Now, what I'm going to do, though, is I'm going to add a couple more features to this model. And these are things that are very idiomatic for F#. So normally I would have done them right off the bat, but I wanted to show a compare and contrast. So now let's do this, but in a more F# way. The first thing I'm going to do is I'm going to add some domain modeling. F# has a very clean, concise syntax for defining types, and we're going to use that to accurately model our domain. And we're going to use units of measure. Units of measure allow us to annotate our numbers with the units they're meant to represent so that the compiler can check our algebra to make sure it's correct. So I'm going to define 2 new types, truck and city, and they are simply just wrapping strings. And so now we don't have just a string hanging out there. We could tell we've given additional context to what this string is meant to represent. I'm also defining some units of measure that I'm going to use to annotate my numbers to make sure that the algebra is actually correct. So now trucks, instead of being a list of string, is a list of truck. And cities is now a list of city. My demand is now a dictionary where the key is the city and the value is a float, but that float is in units of dose. Capacity is, again, a dictionary keyed by truck, but now the value is a float in units of crate per load. Costs, where I have for a given city, for a given truck, here's the cost, but now it's in terms of US dollars per load. And I'm going to annotate my decisions. My decisions are now in units of load. When I do this, I'm going to see some errors appear because I've told the compiler so much more about what this code is meant to represent. So now F# is working for me and helping me to figure out, hey, Matthew, what you're doing doesn't make sense. The first problem is going to be as I index into assignment. If I hover over the C, it's going to say, hey, Matthew, I was expecting truck here, but you gave me a city. Before, assignment was a dictionary keyed by a string tuple. So there was no context for the compiler to say, I don't know, it seems to work, they're all strings. But now that I've embraced F#'s concise syntax for defining types and then accurately modeled the domain using those types, the compiler is now helping me ensure that my model makes sense and how I'm indexing data makes sense. So what I'm going to do now is I'm going to switch the order of those arguments, and now the compiler is going to be happy. This may not seem like a big deal, but when you're doing mathematical planning and you're building models, you're often indexing into multidimensional data. So 2, 3, 4, maybe even 5 dimensions to your data. And keeping track of that in your head is difficult. And then finding the bugs that are caused by indexing by the wrong thing can be very time consuming. So F# is helping me write correct code faster. Now, the next bug is actually even scarier. And it's here. Now the compiler is saying, no, Matthew, this comparison, it doesn't make sense. And I'm like, what do you mean it doesn't make sense? And I hover over it. It says, I don't have an overload for this operator. And what's really important to note is on the left side, it's in units of crate. And on the right side, it's in units of dose. It's saying your units don't make sense, Matthew. Now, if NASA can crash a rover into Mars because of errors with units of measure, we could certainly do it. F# allows me to annotate my numbers to make sure the algebra is correct. And what's even better, there's no performance penalty for this. It's only a compile time check. By the time it gets compiled and goes down to IL, it's disappeared. So I know there's other languages where you can do this type of thing, but it's typically you're adding new types. In F#, you don't need to. It's just as fast. So now I'm going to add a conversion, which is my dose per crate. I'm going to add that multiplication to the constraint, and now the compiler is happy, saying, yep, your comparisons make sense, your algebra makes sense. So why F#? F# allows us to write clear, clean, concise code. It allows us to write that code quickly because it's so succinct in order to define new types in F#. Not only that, it's fast code because it's all running on top of .NET, which is an incredibly fast runtime. And that code is correct because we've accurately modeled our domain, we've used units of measure, and so that code is going to be robust going forward because it's going to be checking, are you using the correct conversions between your units? Are you actually indexing correctly? So that code is going to be more resilient over time. So we spend more time delivering value to people and less time hunting down really painful bugs. Now, to convince you this isn't all smoke and mirrors, I actually have this example fully worked out, and I'm going to send a tweet out here as soon as I'm done with links to both the code of this example and to the presentation I just gave. If you'd like to learn more about F# and mathematical planning, please check out the FLIPS library. It has many more examples across different industries, and it has more details. I can just go in more depth than I can here. Thank you so much for having me. Please feel feel free to reach out to me anytime. I have a blog, MatthewCruz.com, where I'm able to go into more deep detail and work more examples. But I love answering people's questions. Thank you to the organizers for inviting me. It was a real pleasure to come and speak to you today. Thank you very much.
Hi, thank you, Matthew. It was such a great presentation. And
Thank
we're
you.
getting tons of comments from the community on how great your presentation was and your style of presentation and your voice. You're getting like best prize for voice at .NET Conf so far.
Thank you. That's very kind. Thank you.
So let me share my screen and show some of the comments we're getting.
Okay.
So from Kurt, Matthew's talks on mathematical planning with F# and the Flips library is truly mind-blowing. You should look up his talks on YouTube. So I guess you have more talks that people can find on YouTube?
Yeah, I actually have a 3-hour workshop that I gave where I'm able to kind of go from the very beginning and just slowly build up concepts. So yeah, I do have several talks out there and have been planning to do more. I just got back from a month of vacation. My first time I took more than a week off in a few years. And so I just really checked out and just spent time with my family. But you're going to be seeing a lot more coming from me now that I'm back.
Awesome. Yeah, awesome to hear. But we all need a break from time to time as
Yes.
well. So
Yes.
very well deserved. And here's one of the comments about your voice. A bit envious of the tutorial voice and people saying you should do like professional voiceover.
Oh my goodness. Oh my goodness.
Yeah, and then Revan also talking about F# and what a nice topic you just covered. So are there any other resources or things that you think like the community would be interested in learning more about?
So I actually put together a blog post to answer this question. So if you just go to MatthewCruz.com, that first post that's there right now is actually just additional resources for learning this, because there's a lot of different places you can go. The Flips library has a lot of just worked out examples showing you how to do different things. And again, it kind of slowly builds concepts. So between the combination of those things, that's probably the best intro I could give people. Also, please reach out to me with questions. What I'd really love doing is getting a question from somebody. And then with their permission, of course, I like to turn those into blog posts so that I make sure I'm answering questions that people really care about. I'm a deep nerd in this subject. And so I recognize I no longer have beginner eyes, so I don't know what's hard anymore. So that's why I love questions from people so that I can answer your questions and your problems.
Yeah, and Jeremy also saying that he just hopped back into the conference, and the more I see, the more F# is really making sense. And I'm learning tons as well. I'm more of a C# developer myself, but it's been really nice to hear all these presentations today and how you can use F# in such meaningful ways and create really like robust and succinct code that runs really fast and performance. So really, really great stuff happening today. And I don't know if we have our next talk, like next presenters ready. So let's see.
Was I too fast? I was trying to make up a little bit of time for us.
I think we can bring Houston on our next presenter. Yeah, but thank you so much, Matthew. Yeah, you were on time, but we had like a few minutes to kill, and let's see, we got a few new posts, so let's show them. So I'm back, baby.
Nice.
And thanks a ton to Matthew as well for his awesome talk. So yeah, we really appreciate having you here. And with that, we'll bring Houston to talk about some F# tapas.
Awesome. I'm excited. And like I said, I'm on Twitter. I'm on the F# Slack. Hit me with questions anytime. I will get back to you. So thank you so much.
Thank you.